So those you are already done for 1, you can try with number 2. But here, can you guys tell me what is your answer for 1? What is your answer for 1? Let me have a look. Kai Qian, no? How about others? Tony? Wesley? Vashini? Wesley. Wesley, correct. Okay, let me have a look. Tony. Tony, no. Okay, boys and girls. Fastest, that means that related with speed. Am I right? Speed is what? Distance divided by time. A and B. Which one actually will have a greater speed? Faster what? Okay, so greater speed. Greater speed. So which one will having a greater speed? Which one? Okay, so boys and girls, I'm back. Okay. Oh. Okay, so boys and girls, for here, I want to observe displacement time graph is actually, I want to observe one particle only. And then I record down the different times. Okay, can you see that? If one complete wave, how long the time we need? So from here, I want you to calculate it out. What is the period for this graph? Okay, so at here, for example, here, I got the speed. Okay, so did I have the wavelength? Yes, from here I can get the wavelength. So this is wavelength. So V equal to F lambda. Can you help me to find your F? From the F you find, can you find out the time period? T equals to 1 over F. From there, you can know that actually one complete wave, how long the time is needed. How long the time is needed. So boys and girls, I only saw Vashini answer. Any others? Prasan, correct. So Prasan, did I answer your question just now? If asking for the structure question, you mentioned A point is actually larger distance, so you need to travel faster. Okay, Fawao, Kai Qian, Tony, Wesley, Fatima, Joray, Clement. Okay, today we have Clement. Wesley, correct. Kai Qian, correct. Good job. Yeah, Joray, what is your answer for this question? Good job, dear all. So at here, this one is 20 equal to F. Wavelength is 4. Okay, I don't need to change it because this one 20 cm per second. So doesn't matter. I don't need to change it into meter. So my frequency at here is 5 hertz. Okay, so at here is 1 over 5. My period should be 0.2 second. So one complete wave should be 0.2. So this one is wrong. B is wrong. Okay, C is also wrong. One complete wave should be from here to here, actually should be 0.2. But why 4 seconds? No, wrong. So this one also wrong. Answer will be A. Okay, why it would, the shape is like this. Actually here, we can assume at any point, for example, at this point. how this point or this point working. Doesn't matter, you can choose any point. So you choose, let's say we choose this point lah. Let's say we choose this point, okay, the particle at here, how it move. So maybe I choose this so that we can fit to our answer. Okay, so at here I choose this point, which is starting at 4 cm here. Okay, next, how it move. It will go up, it will go down, it will go up, it will go down. Oh, sorry, we choose this point is better. Why? Because later on when it move like this, right? Okay, so this one is going up. Okay, so at here, this point, how this point particle move? It moving vertically. Still remember just now the video, the simulator that I show you. Okay, the particle is moving up, down, up, down. So it will moving up, down, up. Okay, so if let's say I got another graph, it's showing something like this, is it okay? It's fine, actually, it's fine. It can go down first. It can going down first and then going up as long as one complete wave. Okay, but the problem is here, this is not 0.2 seconds, so answer should be A. Okay, is that clear there? C and D, the graph is not good. It's not correct. Okay, we goes to your question number 3. We goes to question number 3. A transverse wave is traveling along a rope. The frequency, once you saw frequency, we can highlight here. There must be some information can be given to us. So from the frequency at here, actually, I know that I can find the period. Okay. The graph show the variation of the distance displacement graph at time equals to 0. So at time equals to 0. Okay. So at here, this is at time equals to 0, it capture all the particle. Okay, so this is the direction in moving. They're asking you which diagram show you the position of the wave when the time is 0.5 seconds. So you have to ask yourself, one complete wave is actually how many seconds? When 0.5 seconds actually is how many complete wave? Half complete wave, one complete wave. Then we can from there deduce now how was your wavefront showing. Okay, so question number 3, can you try? My hint is you find the period first. Find the period, then you will know, compare. When time equals to 0.5 seconds, actually is how many complete wave? Wesley, one of the answer is correct, but you have to determine which one. No. How about others? Let me have a look. Jore, no. Jore, no. Jore, what is the period? Fawal, correct. Fawal, correct. Good job. Washini, Clement, you can join us. You write your answer in the chat box to the Newton. If you message to the Dr. Low, that is my iPad. Prasan, correct. Good job. Wesley, yes. Wesley, correct. Washini, correct, dear. Correct, Washini. Okay, so dear, here, 1 over 2 hertz is 0.5 second. That means that 0.5 second is one complete wave. So after 0.5 second, what does it mean? It will continue another new one. What? It will exactly continue a new one. So at here, your answer actually should be the donkey. Okay? After 0.5 second, actually is exactly, they complete another new one already. Okay, like something like this. What? Okay, for example, like this, 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 whatever. Okay, initially it's like this, okay? So it start to move. After 0.5 second, it will complete one complete wave. Okay, it will travel one complete wave. So that means that right now, can you see that? It's actually the same wavefront. Actually, the same wavefront. The front one, actually, they will come back. Maybe we can do like this, okay? The whole part is like this, okay? So after 0.5 second, the whole wave will travel one complete wave. Will travel one complete wave after 0.5 second. So look at here, okay, look at here. Initially capture like this. Then after 0.5 seconds is one complete wave. We're already traveling one complete wave. Traveling one complete wave. So the answer should be donkey. Answer should be donkey. Because here 0.5 is actually after one complete wave. Is that clear? Is it okay, dear? Fawa okay. How about others? Kai Chen okay. Kai Chen okay. Vashini okay. Tony okay. Okay, good job. So boys and girls, we go to next page. Question number 4. Progressive longitudinal wave. Progressive wave can be transverse wave, can be longitudinal lah. Okay. So for this one is from here we can determine some compression and rarefaction. Okay. So a progressive longitudinal wave travels through a medium from left to right. So this is figure 4.1 shows the position of some of the particle of the medium at time t equals to 0. Okay, at time t equals to 0. Then a graph showing the particle displacements at the same times t equals to 0. So this is displacement distance graph showing at time t equals to 0. Then all the particles, they are in this position. Okay. So particle displacement to the right, okay, particle displacement to the right of their equilibrium position are shown as positive on the graph. If displacement is goes to the right, that means that this is a positive, okay, displacement is positive, then in moving positive, then we move to the right. Okay, particle displacement to the left are shown in the negative of the graph. So that means that this part is going to the right. So negative area is going to the left. So this is displacement positive, displacement negative. Okay. Period of the wave is t. On the figure 4.1, draw a circle around two particles which are exactly one wavelength apart. So you want to know one complete wave. From where to where? Longitudinal wave, we got compression, rarefaction, compression, rarefaction. So from where to where is one complete wave? We can choose compression to compression. Compression to compression is considered as, okay, one complete wave. So they're asking you to draw circle around two particles. Which two particle position? Okay, they are exactly one complete wave. Yes, okay, one wavelength lah. Okay, one wavelength. So you look at here, all these particles from the positive area, they move to the right. Can you see? Move to the right. Negative area, they move to the left. That's why we form this pattern. So from here, I can exactly know that point X at here is compression, right? Compression. Then this one positive goes to the right, goes to the right. Here just now goes to the left, here goes to the right one, right? Here negative goes to the left, positive goes to the right. So at your point Y at here, actually is called rarefaction. Okay, then until here again, this is compression. So from compression to compression, this is one complete wave. From here to here is one complete wave. Okay, so at here, which particle? We can circle this particle. We can circle this particle. These two particles represent are exactly, their distance is exactly one wavelength apart. Until here, okay? Okay, Fawa, Wesley, all okay, If not okay, you private message me, then I will trying to help you, okay? So at here, on figure 4.1, sketch a line on the graph to represent the displacement of the particle for longitudinal wave at time t equals to 0 plus t over 4. T over 4, dear, T over 4. That means that just now, we want complete wave run. Let me draw, maybe I draw like this. Okay, so this one. Okay, you see, just now, this one, if one complete wave is we move exactly one complete wave, right? This is one complete wave. Okay, if half complete wave is like this, do you agree? Half. So this one, from here to here is called half. Then 1/4, 1/4 actually should be like this. It should be the wave, new wave front actually should be like this. My blue color. Okay, my blue color line. So just now the 2 point you have to ignore. Wait, let me erase first. This one erase first. One more time. I draw the line. Here, 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 here. Okay. One more time. If moving, half wavelength is this. Half wavelength is this. Okay. Because from here, this one is compression, here is rarefaction. Okay. So from here to here is actually half wavelength. Half wavelength. Okay. So from rarefaction to rarefaction actually is another one complete wave. Okay, so you look at me here, the wave front. Okay, at start is not moving. So at here, t equals to 0. So when t equals to complete wave, one complete wave is period t. After t, actually, I will move until here. After t, I will move until here. Period is t. See here, period is t. So after t, actually, I will move exactly one complete wave later. Okay, so that means that half complete wave is this. So when t divided by 2, that means that half complete wave, I will move until here. Okay, then 1/4, 1/4, then we have to 90 degree lah, move forward a bit, like this. So my blue color line actually is your new wave front. Okay, your wave front, new wave front, yeah. Sketch a line on the graph to represent the displacement of the particle for the longitudinal wave. So this one is actually, okay, the TO plus T/4. Then just now this one and this one is to represent one complete wave. Okay, for 1 and 2, is that clear? 1 and 2. Question 1 and 2, is it okay? Okay, Okay, then we look at the number 3. State the direction of motion of particle Z. How the particle Z is moving. Okay, so at here, the particle Z, how it moves. Wait, let me have a look. Particle Z is somewhere here, right there. Particle Z is somewhere here. Particle Z is still at the positive displacement. Particle Z is still at positive area here. Okay, so how it move? It will move to the right. Okay, state the direction of motion of the particle Z at time t0 plus. T over what? 1/4. 1/4. 1/4. Okay. Okay, so at here, we look at the new wave front at here. The Z position is still at the positive displacement. So how this particle moving? It moves to the right. Z particle motion is moving towards to the right. So at here we write down towards right. Okay, for this one, can you get my idea? Do you able to get my idea? Z point after 1/4 complete period, okay, 1/4. So it's still at the positive displacement. So how it move to the right? Okay, so the frequency, again, frequency is F. Okay, the distance between X and Y. Where is your X? Where is your Y? Okay, X and Y here. Distance between X and Y is actually 0.19. 0.19 meter. Okay. They're asking you to find the speed. Okay, here, boys and girls, we got frequency, we got the certain distance. But we found out that X to Y, this is not a complete wavelength. It's not. Can you using the formula to find the speed? Speed equals to F lambda. Can you try before I give you the answer? You got the frequency, find out the wavelength, then you can substitute and find out what is the speed. For me, count it up. Final answer for me. Don't have my calculator. Okay. Heartbroken. Okay, Vashini. Yes, correct. Vashini, correct. Okay, so boys and girls, frequency is 16,000 kilo. Don't forget about the prefix. Kilo is 1,000 times the wavelength. You look at here, x to y actually is half wavelength only. Compression to refraction is all. Okay, for this question number 4, before we proceed to the lesson number 35, any question? Any of you facing any problems? If no question, can you give me reaction at the bottom part audio? T equals to TO. This graph is actually T equals to TO. It captures at certain moment here. T equals to T0. Okay, Wesley here, T equals to T0. Then after a moment, sometimes of TO, what is the sometimes? One complete wave is T. One complete wave is T. Then T over 4, you can think like 90 degree. Okay, you move. One complete wave is 360 degree. We move. Using degree not good. You will confuse. Okay, it's okay. So at here, starting here, this black color actually is T equals to TO. After one complete wave T, after a period of T, actually your wave initially it's like this. So it will start to travel. It will start to travel. Okay? When it travel until here, actually is already after one period. Do you agree? It will travel from here, travel until here. It finish one complete wave. Actually, your period is called T. Period is called T. After T, actually, it will comes to here. Am I right? Okay. Then after T plus T over 2, that means half of the wavelength. If half of the wavelength, it should be it should be somewhere here. Okay, half of the wavelength, because this is half of the wavelength. Here is half of the wavelength. Okay, if half of the wavelength, the wavefront pattern actually should be like this. Okay, if half and half again, that means that T equals to 1 over 4. Okay, so that means that you move forward again. So at here, this is the new pattern. Of course, the front part, if you want, you can continue to complete it. No problem. Okay, but I just trying to move it and letting you to see how was the wave front pattern actually will performs. Okay, so at here, this one is actually where? Okay, here. Initially it's like this. Okay, initially it's like this. So this is T over 4. This is T over 2. This is 3 over 4T. This is one complete T. If after a period T, actually you are repeating the same wavefront pattern. You are repeating the same wavefront pattern. Okay? If one complete wave T period, actually you'll get exactly the same. So there is no difference with the original wavefront. But if you are half of the wavelength, two wavefront pattern, waveform pattern, it will be exactly like this. If 1/4, then it will be different like this. Wesley, you digest. If still cannot, then maybe I trying to find something to explain to you after that. Okay, I trying to find is there any video can understand. Oh, good job, dear. Okay, dear, if okay, then we goes to the lesson number 35. Okay, we goes to lesson, oh no, not 35, that is my school worksheet. Okay, we are going to the lesson number 29. Phase and phase different. Okay, we goes to this. So before that, actually later on it comes to here, maybe you can understand a bit. Okay, here. Phase actually is we talking about how far through a circle of the wave is. Okay, in another way, I can be explained that position of the particle. We can say that phase is actually talking about position within one complete wave, complete oscillation. Okay, how far the point actually moving, okay, through its cycle, how far the point is moving. Okay, so at here phase different, we are finding the difference between two waves. It can be two wave, it can be same wave but different particle, no problem. We find the phase different. Okay, so at here the blue color is leading wave. Okay, if there is a leading, okay, this is the crest or trough will be produced earlier than another one. So the green color actually is lagging wave. We want to find how big difference, okay, the phase difference between them. So how are we going to count the phase difference? Okay, the phase difference can be measured in angle or measured in fraction. Okay, so a full cycle, we can say that is wavelength. Half cycle is 1/2 wavelength. Angles can be measured in degree or radians. So we can say that if it is repeating exactly the same, actually there are zero phase difference. Okay, this one later on we'll talk. Okay, so at here, 0, 90, 180, 270, and 360. Okay, so this is considered one full cycle, one wavelength. See here, one wavelength. Okay, we want to find the phase difference between two particles at here, two particles. How are we going to find? So at here, you need to find the difference between these two waves. Distance between these two waves divided by their wavelength times, depends on you want degree or you want the radian. If you want the radian, then you times 2 pi. Okay, so in time. So the question asking you, what is the phase difference between point P and Q? So they are finding this point and this point. Okay, my question is from here to here, how many complete wave? What is the distance between them? Okay, just now we say this one is okay, if you are exactly same shape like me and like this, okay, exactly overlap. So I say that you and me are in phase. We are 0 degree phase different. But if my red color at here is after one complete wave like this, okay, so I can say that we are 360 degree in difference. Can you see that this one? 360 degree phase different. I'm here and you are here. We are different is 360, but we still in phase, we're still in phase. Okay, I'm at this position, you are at the same position as me, so we are in phase. Okay, so in phase, that means that if I'm at crest, you are also at crest. I'm at trough, you are also at trough. Okay, if the two particle that oscillate at anti-phase, anti-phase. So that means that if let's say I'm like this, you are opposite to me, okay, opposite. So you are 180 degree. So at the end, you might be opposite way from me, okay? You are maybe here. Wait. No good. Okay, ignore this. Okay, we look at here, example more better. We look at the example here. Point A and B, can you see that? They are exactly at the same position, same point. Okay, from here A to B actually is one complete wave. Okay, this is one complete wave. So we can say that A and B actually they are in phase. They are in phase. Okay, they are in phase because they are at the same position. If let's say I continue drawing my graph like this, I add a point at here called E. Then my C and E actually are in phase. I'm at crest, E point also at crest. So I say that they are in phase, okay? So C and D have a phase difference of 90 degree. How I know it's 90 degree? Okay, C and D, C and D. So we look at C and D here. Okay, what is the difference between them? What is their X? This one, we put it as X. Okay, then from C to E at here is actually one complete wavelength. So from C to D is actually how far the distance. What is the X? So this one, C and D phase difference is what over the wavelength times 360 degree. So you look at here, from here, 0, 90 degree, 180 degree, 270 degree, 360 degree. So this one to here is 90 degree. Here 90 degree, another 90 degree, another 90 degree, and here another 90 degree. So 90, 180, 270, and 360. So from C to D, actually the difference is actually 90 degree. Am I right? Actually, it's 1 over 1 over 4 wavelength. 1 over 4 wavelength. Right? This part is 1 over 4 wavelength. Here to here. Here is 1 over 4 wavelength. Okay, so if you do it and at the end, you'll get 90 degree. Or using the way that I mentioned just now, this is one complete wave. One complete wave is 360 degree. Half of it is 180 degree. Half of it is 180 degree. Then half again, this is 90 degree. So what is the difference between C and D? What is your phase difference for C and D? Answer is 90 degree. Okay, then we say that they are not in phase. In phase is they are same phase right now. I'm at crest, you are at crest also. When I going down, you're also going down together. Okay, so we goes to your page number 3. Boys and girls, we goes to page number 3. This one okay or not? It's new thing for you. That's why need some time to digest it. Need some time. But later on, when we do the past year question, we will make it more clear lah. Okay. Diagram below shows that the green color, okay, lead the purple color by 1 over 4. 1 over 4, that means that 90 degree that is lead 90 degree. So can you see that this one and this one is actually 90 degree different? Okay, 1 over 4 different. Or you here, see? This one is showing you 1 over 4 wavelength different. Okay, from green color at here like this is called one complete wave. Here is called 1 over 2 wave. So here is called 1 over 4 wave. What is the difference between green color and purple color is 1 over 4 wavelength. Anti-phase and not in phase is same thing, right? Not in phase, actually it can be others angle. Okay, anti-phase is exactly opposite to it. Totally opposite to it. Okay, so boys and girls here, I explain one more time. If I look at the green color here, trough to trough, this is considered one complete wave. Here to here is one complete wave. Okay, half of the green color at here is 1 over 2 wave. So half again, this is 1/4 wavelength. Okay, so I know that what is the difference between the green color and purple color? They are 1/4 wavelength. They are 1/4. Okay, 1/4 times 360, I know that they are 90-degree difference. Actually, it's like this. They are using 1/4 wavelength divided by wavelength times 360. Wavelength and wavelength cancel, so they get 90-degree. Actually, this case is same like just now. Okay, we're finding out how far different, the phase different. You can make it in the fraction, you can make it in the pi, okay, radian, degree, and also fraction, no problems, okay? So at here, we try with the partial question, apply the formula just now. What is the phase difference between two? Phase difference is x distance between two divided by the wavelength times 360 degree. So boys and girls, can you try? Can you try? What is the distance between them? And then what is the wavelength? Then times 360. Then I know, okay, what is their difference. Fawal correct. Jore correct. Jore correct. How about others? Difference between these two position, okay? Two ball, okay, difference between these two ball. So difference between these two ball is 1.3. What is the wavelength? What is the wavelength, dear? How we know the wavelength? Prasan correct. Okay, this is the crest. This is the crest. So another crest, it will be here. Am I right? Another crest will be here. From here to here, it should be a complete wave. This one should be a complete wave. But what is this? Can you see that? At here is trough. So from C crest to trough at here actually is half wavelength. 0.9. So one complete wavelength actually should be 1.8, or we say 0.9 times 2 times 360 degree. So did you get my idea there? From here to here is actually half wavelength. But I want to know the full wavelength, one complete wavelength. So from crest to crest, so this is the one complete wavelength. You should using 0.9 times another plus another 0.9. So it's actually 1.8 lah. 1.8. Vashini, correct. Answer is donkey. So boys and girls, answer should be donkey. 260 degree. Okay. So can you try with the question number 2? For this question, any of you still facing any problems? Any of you facing any problems? Okay, Fawa, okay. Wesley, okay. Tony, are you here today? Jore, okay. Fatima, Fatima. Kaichen, okay. Okay, then we go to your next page. Clement, okay, good job. Okay, here two wave pass through Fatima, okay. Two wave pass through point P. The graph showing, okay, the two wave at point P. The phase difference between the two wave at point P. So at point P, they capture these two waves. They want to find their phase difference. Okay, what is their phase difference? So at here, from crest to crest, easy, I will trying to find from crest to crest here. Crest to crest here. I'm trying to find this one, how far they travel, how far they separate. Okay, what is the distance between these two waves? Okay, then after that, you have to find out what is your one complete wave. What is your one complete wave? Okay, so for this one complete wave, we can say that this is one complete wave. Okay, oosh. Wait, here, going down, going up. This is one complete wave. Okay, so from here, go here. This is one complete wavelength. Okay, so at here, what is the how far different between them? The equals to different, then one complete wave. Although this is time lah, but we can use it times 360 degree. Okay, let me check. Prasan, answer correct, Prasan. Fawa correct. Vashini correct. Okay, so at here, our answer it should be here difference. Okay, how big difference? It's only one box. Okay, this one X is only one box. Then here, one complete wave is actually 8 box. We got total 8 box. Okay, so at here times 360 degree, you will get 45 degree. Okay, 45 degree. So I need to check. Well, let me have a look. Let me check. Okay, we were trying to find two crest, two same point. How to know the difference is one box? Here, boys and girls here. Okay, from crest, I choose crest. This one, my wave. Okay, I choose this wave and this wave. What is their difference? So I choose the same point. When I'm at crest, where is you? Where is your crest? So at here, this is one box difference. Okay, because this is time. So I don't say that this is wavelength lah. Okay, this is one box difference, or maybe you can say this is 1 second difference. 1 second difference. Okay, 1 second difference. Okay, one complete wave is this blue color. This is one complete wave. It actually took X second. So you are lagging 1 second. You are lagging 1 second than me. Wesley is lagging 1 second. When I crash, my crash actually is after you 1 second, after your 1 second. So I'm lagging 1 second. Then the wavelength is actually not wavelength. One complete wave is X second. A period for one complete wave is X second. So 1 second over X second, our difference is 45 degree. Wesley, do you get it? You find crest to crest. Okay, you find crest to crest. Crest point for one wave, another crest point for another wave. I want to find their difference. So I found out that I was 1 second lagging. Okay, 1 second lagging. So boys and girls, yes, Wesley, okay. We go to question number 3. Progressive radio wave frequency. This is the frequency. What is the phase difference? What is the phase difference? We want phase difference is how far the difference and divided by wavelength times 360. They say that 2 points that are 50 cm. So this should be my X. 2 points, they are far away 50 cm from each others. But the problem is you already know the 50 cm. Do you know the wavelength? Do you ever to calculate the wavelength? This one actually involved with your year 10 knowledge. Year 10 knowledge. You got the frequency. I want to know the wavelength. I know the frequency 75 mega. Mega is times 10 power of 6. Times 10 power of 6. This is mega. I want to find the wavelength. Teacher, I don't have the speed of radio. What is the speed of radio? Jore, correct. So how about others? Yes, Jore, very good. Speed of the radio. This is under EM wave. EM wave, we got what? Ramly make Indian vegetable unto ex-girlfriend. We got this 7 wave. Radio wave is one of them. This is called visible light. How fast the light travel? 3 times 10 power of 8 meter per second. All these EMF, they are EM wave. They are same family. How fast you travel? It's me. Also my speed. Okay, we are the same. So for this radio, how fast it travel? 3 times 10 power of 8. They don't tell you and they assume you know that. Okay, they assume you know this. Very good, Vashini. Prasan, very good. Okay, so from here, you can calculate your wavelength. So you do substitute. Don't forget the wavelength that you get at here actually is in meter. Why? Because this one, the unit for 3 times 10 power of 8 is meter per second. Frequency is in hertz. These two are SI unit. SI unit. That means that the wavelength that you get also SI unit. You see, 3 times 10 power of 8 is meter per second. Meter is meter. So at here, I get 4. So over wavelength is 4. How far they different? 0.5. meter, convert to meter, times 360 degree. So actually our answer should be 45 degree. Fawal, no, Fawal, check the working step. Kai Chen correct. Clement correct. Yeah, Fawal, check which part you make mistake. Okay, boys and girls, we go to number 4. Question number 4. Can we proceed for this question? Okay, good job. We go to question number 4. Okay, in a progressive water wave, two particles P and Q on the surface of water are fixed horizontal distance apart. P and Q oscillate vertically. Okay, they oscillate up, down, lah. At time t equals to 0, so this is the wave that capture. Okay, which graph will base represent the variation with time t of the phase difference? So phase difference against t. Okay, so at here, phase difference is actually how far they different divided by wavelength times 360 degree. This question not easy, but let us see. Any of you can able to get the answer. What do you think? X is the distance between these two. It's called X. This is the X. Okay, so this particle will moving up, down, up, down. Okay, this particle Q also moving up, down, up, down. The wave will travel along this, okay, going to the right. So I want to ask you, what is their phase difference from time to time? Let us see any of you. Oh, very good, Prasan. Your idea is very good. Yes, if you're able to answer correctly, then that means that you really understand. Wesley, correct. Wesley, correct. Jory, no. Jory, no. How about others? Try. No need to be shy to try. We don't know each others. Jory, correct. We don't know each others. I don't know. I don't know you at all. Only you saw me. Wesley, correct. Wesley, correct. The explanation is correct. Fawal, no. Okay, from time to time. From time to time, does their x changes? The x different, will the x different changes? P and Q position, they are fixed. Am I right? They only vibrate up, down at their own position. Am I right? P particle only move up, down, up, down. Recall back starting the simulator that I show you. The green color particle only move up, down, up, down. Another green color also up, down, up, down. So their distance all the time are the same. Do you agree? No matter you start your stopwatch for how many seconds, this P will always up down at here, Q always up down at here. Their distance between these 2 points never be changed. Am I right? Kai Chen correct. So at here, P position and Q position are fixed. So these two positions are fixed. So their phase difference for X is fixed, is constant, in unchanged. So wavelength also unchanged. So at the end, this one is actually a constant value. Nothing changed. Your answer should be Fawal correct right now. Vashini correct. For this question, our answer should be donkey. For this question, our answer should be donkey. Clement, correct. Clement, correct. So you guys get the idea. No matter how you, from time to time, you change. The two particles, they just at their own place, up, down, up, down. The distance between them doesn't change at all, dear. Doesn't change at all. Is it okay? Can we proceed to the next question, dear? Yes or no? Yes, Vashini, Wesley, Tony, Kai Qian, Fawal, Clement. Okay, then it goes to the next page. Progressive wave travel from left to right. Okay, this is the part of the string at one instant I capture at certain moment. Kata, all the particle I capture it down. P, Q, R are three different points. The distance between P and R is 0.48. Can you determine the wavelength? Easy lah, dear. No need to guide you. Do it and tell me what is the wavelength. 0.48 is not one complete wave. It's not. So need you to find it out. One complete wave actually is how many meter? Vashini, let me have a look. Very good. Very good. Jore, very good. Correct. How about others? Only two of you able to solve? Impossible. You guys are smart people. What? You can do it, dear. Wesley, correct. Wesley, correct. Be confident. Prasan, correct. Wesley, don't forget about the unit. Okay, here, boys and girls. Okay, from trough to trough is one complete wave. Then trough to another crest. Actually, it will be half of it. So, Fawa, no. Okay, so at here, actually 0.48 is 1.5 wavelength. It's 1.5. Supposedly going down here, this is another one complete. So this part is actually half of it only, half of the wavelength. Half wavelength. So from P to another trough to another trough is actually one wavelength. So 1.5 wavelength showing you 0.48. Wavelength showing you 0.32 meter. 0.32 meter. Okay, Tony. Yes, correct, Tony. Okay, can you try? What is the speed? So V equals to F lambda. So you already got the wavelength. Can you find the speed? But the problem is how you know the frequency. Find the information from the upper part, from the sentence, from the questions. So you find your frequency. And then the wavelength, you use the wavelength just now given to you. You calculate one, not given to you. It's you calculate one. Yes, correct, Prasan. Correct. Vashini, correct. Very good. Tony, yes, Tony. Fawa, correct. Kai-chen, correct. Good job. Okay, dear, here. Frequency is 1 over period. Because here they're giving us the period. So 1 over 0.02. So at here, oh, I don't have calculator. 1 over 0.02. Wait. 50. Okay, 50 hertz. So at here, 50 times the wavelength 0.32. My answer is here is 16 meter per second. Okay, 16 meter per second. Okay, the last one is the main thing. Okay, the first and second, actually year 10 we can solve one. Okay, here determine the phase difference between Q and R. Can you find out what is the phase difference between these two? How far they separate? In the degree, in the radian? Prasan, no? Prasan, no? Wesley, correct. Wesley, correct. How about others? Jore, correct. Kai-chen, try. Clement, try. Tell me your answer. What is the phase difference between Q and R? How far they separate over their wavelength? Phase difference is how far they separate over their wavelength times 360 degree. How far they separate? Fawal, correct. Prasan, correct. Vashini, correct. Oh, good job. Tony, no, no, no. Tony, no, no, no. Clement, no. Clement, no. Okay, here, I give you some hints. You see, from here to here is one complete wave. They already greater than one full cycle, one complete wave. That means your answer should be greater than 360 degree. It must be greater than 360 degree. From here, it already far apart from each others for one complete wave. One complete wave is 360 degree. So how far difference between them? Kai Qian, no. Okay, so at here, this one until here is one complete wave. Then this one is another 0.25, 1 over 4 lah, 1 over 4. Clement correct right now. Yes, Clement correct. So boys and girls, from the x at here, I can say that their difference is actually 1.25 wavelength. 1.25 wavelength. Okay, from R to R here is considered one complete wave. From here to here is one complete wavelength. Okay, so how far different between these two? Okay, I can continue draw my graph something like this. Okay, crest to crest is one complete wave. Half of it is 1 over 2. Half again, so that means that this one is 1 over 4 wavelength. 1 over 4 is actually 0.25 lah, 0.25. Tony correct right now. Fatima, no. Fatima, this is only difference one wave is 360. So it will be slightly greater than 360. Their difference is more than one complete wave. So it will be greater than 360, but slightly greater than it. Okay? Kai Qian correct. Okay, maybe I can draw in this way. Let me clean. Let me draw. Here, okay. Let's say my graph is from here to here, okay, like this. Whoosh. Why here? Okay. Here to here is considered one complete wavelength. Half of it, if here, half of it, then this part will be 1 over 2 wavelength. Then if here, half again, which is my distance is here, okay, this graph is like this. Okay, so that means that half of it, and then this is another half of it. Another half of it. So from here to here, actually 1 over 4 wavelength, which is 0.25 wavelength. You look at me, this one, this part is actually my part here. How far different for this part is 0.25. Then total from R to Q is actually 1 over 25. This is 1. This is 0.25. So actually, how far different between QR and between point Q and point R is actually 1.25 wavelength. This part here, this part actually is the part that I'm showing here. I make it crest to crest is one complete wave. From here to here is one complete wave. Okay, half of it is from here to here. Half of it is 1 over 2 wavelength lah. Then half of the 1 over 2 is 1 over 4 wavelength. So this part is actually 1 over 4. Okay, this answer from the answer screen is 450 degree percent. So it's because it's already greater than one complete wave. So your answer should be greater than 360 degree. Okay. So just now the Prasan asking me question. You guys don't listen first. I explain to Prasan. Okay, Prasan, you look at here. If this one, I always say that we choose crest to crest. So this is the distance that we want to find. So maybe you will think, teacher, can I using this crest to another crest at here? If like this, your answer will get more than what we get. Okay, this is big difference. Okay, you using this one, the blue color crest to another crest for behind one. If like this, your answer will be very big. So for us, if we want to finding the phase difference between two wave, we choosing the closer one. What is their difference between the closer crest and crest? We don't the 60 degree. So our answer at here, it will be 1.25 wavelength divided by wavelength times 360 degree. So this answer should be 450 degree. It's already greater than one complete wave. Confirm it's greater than one complete wave. So this answer actually is for your number 3. Question number 3. 1, 2, 3. Answer is here. 450 degree is obviously greater than one complete wave. So answer must be greater than 360 degree. Okay, so how I know the difference between these 2 points? This is one complete wave. This is 1/4 complete wave. Why? Here I drawing out one complete wave. So half of it is actually half wavelength. Half again is 1/4. So my green color, this part actually is 1/4 wavelength. Okay, can we proceed to the page number 7? Aichen, okay. Washini, okay. Fatima, okay. Wesley, okay. Fawal, okay. Tony, okay. Tony. Prasan, is it okay? We cannot accept with the 90 degree, because it's obviously lagging one full wave. Clement, okay. Prasan, okay. Okay. There we go to your next question. So this is the displacement of the wave x passing through a point. Okay. So intensity. Oh, intensity is related to what we learned in last week. Last week we learned. Okay, here. Let me have a look. Okay, here. Determine the frequency. Easy lah, frequency. You guys do it. Frequency from the graph you can determine by using the period. Haha, Wesley, I will deduct your mark. Wrong. Remember, there is no fraction in final answer. No fraction. But your answer still wrong. Wesley, your answer still wrong. Washini, correct. Okay, dear. We need to find the period. Period is crest to crest. This is called period. Period is 4 millisecond. Period is 4 millisecond. So at here, frequency is 1 over period. Period is 1/4 times 10 power of -3. Wesley, you didn't do this part. Times 10 power of -3. Read meter second. Yes. Millisecond. Correct, Fawal? Jore, correct. Okay, so at here, you will get 250 hertz. Don't trying to stop your answer in the fraction. In physics, final answer, no fraction. So 250 hertz. Okay, a second wave Z. Oh, we got a new wave. They're asking you to sketch the wave Z. With the same frequency. If same frequency, that means at here we label same period. Same period. Label same period. As the wave X pass through the point P, wave Z has an intensity 2I. Okay, intensity is directly proportional to your amplitude square. You can refer to the last week lesson. This is the formula when we're talking about the intensity. Phase difference between them is 90 degree. Phase difference between them is 90 degree. Okay, this is one complete wave, which is 360 degree. Like this. It's called 360 degree. Okay, if half of it from here to here is called 180 degree. 90 degree is somewhere here. 90 degree is somewhere here. Okay, from here to here. From here to here, which is 90 degree, something like this. Okay. So on the figure 5.1, sketch the variation with time t of the displacement y. Okay, so at here, wave z, we got 2I. Okay, we got 2I. It's directly proportional to AZ2. Okay, this is new amplitude. New amplitude. Actually, we want to trying to find the new amplitude lah. Okay, so I can make this 2 2i ratio, we make a ratio, 2i. This one just now, this is with zx, with x. Okay, now we increase the intensity. We want to see how the amplitude changes. So basically, we want to find what happened to this. Okay, so at here, 2i over I. Okay, here directly proportional, actually we can make a formula, we can make it equal to add one more constant value so that we can get this kind of formula lah, okay? We can change this directly proportional to equals, then put a constant value for it, okay? So at here, this one 2i, so this one kaz square divided by ka square. So at here, we can cancel out the k and k. Okay, then the az, what is your new az? Az square equals to I, and I can cancel. So this one is 2a square. Wait, let me have a look. 2. Amplitude. Oh, what is your amplitude for your x? What is your amplitude for your x? We come here. What is your amplitude for your x? So this is your amplitude for your x. With x is 2 cm. So I want to know right now how many cm for my new wave. So at here 2 square. Okay, so az square equals to square root u2 square. Is it correct? Let me press my calculator. Okay, here. It should not be right a square anymore. Okay, like this. Let me check. From here, okay, from here, I know that my new amplitude for wave jet, it should be 2.x cm. Until this step, do you guys understand what am I doing right now? I want to know the new waveform, okay, wave patterns for the wave Z. Wave Z having intensity double 2i, but I don't know what is this new wave amplitude, okay? So I make a ratio to find it out in terms of wave X. What is my amplitude for my wave Z? So at here, my az square equals to, this one can cancel, we cancel lah. So I get 2ax square. Ax is just now the wavefront, the amplitude is 2 cm. So I put my 2 cm in here, square it. So at the end, I knew that my new wavefront with double up intensity, I will get a higher amplitude. Because intensity in amplitude, they are directly proportional. What? If you're increasing your intensity, your amplitude must be increased also. How much we increase? This is the part that we should do calculation. Okay, is it okay? Until here, okay? Okay, Okay, so I know that I should draw my amplitude, which is 2.8. Okay, which is 2.8. So I roughly draw 2.8 somewhere here. This is our maximum. Then it should be like going down, then going to the 2.8. You don't draw. This is not final answer. Oops. Something like this. 2.8 going down here. Then after that, from here, going down to 2.8. Okay, from 2.8, I go back. This is not my final answer. You don't draw. Okay, like this. Okay, boys and girls, my wave Z, actually, it should be get something like this. Higher amplitude, because my intensity is higher one. So I trying to draw 2.8. Cannot see. If cannot see, I change again. I using others color to change. Okay, 2.8 somewhere here, going to here. Okay, from here, going to 2.8 somewhere here. Okay, from here, I go back. Then from here, I goes to the 2.8. Where is my 2.8? Is it here? I think so. Here, going down. Okay, boys and girls. of course, I draw not that nice, no sharp one, You need to draw a nice one, okay, dear? Okay, boys and girls, here. This is the new amplitude. You don't draw the sharp one, you have to smooth, dear. Okay, next. What I want to say? Oh, okay. We know the amplitude already, but why I know I can having the same period is because just now they got mentioned. Where they got mentioned? I think they got mentioned. Same frequency, dear. Here. They're having same frequency. So I need to have a same period. Okay, one complete wave. The time for one complete wave must be fixed. Must be the same. Okay, must be the same. So right now, there is another things. Phase difference is 90 degree. Phase difference is 90 degree. How we move, okay? So at here, okay. So if like this, where from here, we go one complete wave, which means that come here is actually 360. Half of it actually is somewhere here. Am I right? Then 90 degree, where is it? It's here. Do you agree? We move 90 degree, okay, from here. Okay, maybe I can draw in this way. From here to here is 360 degree. Crest to crest, what, right? Then from here to half of it, this is called 180 degree. Then 90 degree, you should move like this, 90 degree. So basically, I should draw my wavelength or wavefront, wave pattern, not wavefront, wave pattern or waveform. I should move 90 degree to here. You get what I mean? So if I complete my wave, it should be like this. But the sharp one not nice. My graph not nice. Allow me to redraw my graph. But the idea is like this. Do you get what I mean? It moved 90 degree backwards. Lagging 90 degree. One complete wave is 360 degree. One complete wave is 360 degree. So we are going to lagging only 90 degree. So you move it. Okay? Half of it is 100, 180 degree. So half of 180 degree is 90 degree. Okay, so allow me to redraw my wavefront. The sharp one very ugly. No, that is not what I want. Okay, let me draw it out. So I will be from here. Goes to the 2.8. Wow, so hard to draw from here and then going down. I want a longer line. It's so hard for me to draw. Try my best. Okay, 2.8. Okay, guys, did you get what I want? My iPad so hard to draw, but did you guys get the idea how I'm going to draw it? 2.8. I'm going to crazy. Something like this. Then continue another 2.8. Okay. Like boys and girls, did you get my idea? So start at 0. Yeah, I complete it. We assume that it moved backward. They are both 90 degree difference. Crest to another crest, there are 90 degree difference. So we are identifying crest to crest is 360 degree, half of it 180, then another half is 90 degree. So I move my wavefront 90 degree backwards, lagging 90 degrees. So I write down this is my wave Z. Then how I know the period? Because it will be the same period as just now, which is 4 milliseconds as one complete wave. So you see my one complete wave. is 4 millisecond. Correct. Amplitude is based on just now the intensity. Intensity formula, you can refer to the last week one. Okay, last week we learned about intensity is directly proportional to the amplitude. Intensity higher, amplitude will be higher. From there, we know that our new wave pattern, not wave pattern, it should be having an amplitude of 2.8 cm. Okay, any question for this question? Wow, very good. How about others? If you got question, no need to shy to ask me. If you really shy at here, you find my WhatsApp and then you message me, okay? Kai Chen, okay. So boys and girls, if okay, the behind actually is self-practice. So you can do it by yourself. Answer is provided at the bottom part at here. So Clement, answer is here. You can try and then you try to check the answer. Okay, if no question, we are going to the lesson number 30. Doppler effect. Can we go? Have you complete? Then we go to lesson number 36. Okay, so let's go. Doppler effect. Okay. So boys and girls, the siren of the ambulance appears to decrease in frequency. The sound will be lower in pitch if decrease in frequency. Then this one is our year 10 we learn, okay, about the sound. Frequency lower, pitch is actually lower. Okay, pitch is related with frequency lah. As it move further away from you. If it moves close to you, then the frequency will be increased. So that means that the frequency that we observe, we are the observer. Ambulance is the source. We are the observer to observe the sound, the wave. We will find that the frequency will change. Actually, the frequency change is because there is a motion between the source and the observer. The ambulance move towards to me. I'm the observer. So the source coming and we have in between us, we have relative motion. So because of this relative motion, either it's moving towards or away, so they will having a change of frequency. The frequency change we call it as Doppler effect. Okay, Doppler effect. So this one why I put in the box, because past year question they ask, can you describe Doppler effect? So this is the answer. Can you describe Doppler effect? Answer is observed frequency is different. What we observe, we are the observer, observe the frequency, we will get different frequency. Okay, it's different from the source, different from the ambulance frequency. The frequency that we observe, it will be different with the source at the ambulance. When the source is either moving towards or away towards us or away from us. Okay, okay. So funny. Okay, here again, one more time, we are the observer. The ambulance is the source. The frequency that we observe will keep on changing when the ambulance is either towards us or away from us, because there is relative motion. So this one is when they're asking you how to describe Doppler effect, this is the answer. Okay, we look at here. When both stationary, the ambulance and you are the observer, you standing there. Then the ambulance actually not moving, I'm also not moving. Then actually at the end, the frequency does not change. They were having all the time is the same frequency. Wavelength also the same. Okay, then after that, when the source move towards you, you are standing at here, ambulance move towards you. You will find that the wavelength, this is called wavefront. This is called wavefront. The circle is called wavefront. Wavefront distance between wavefront is called wavelength. Okay, so this one is wavelength. Here is wavelength. You will find that the wavelength is decreases compared to just now. Okay, compared to just now, here is the wavelength. Now the wavelength become decreases. If you are away, this is away, this side is away, this side is away. Here, this side is towards. Okay, so if away, your wavelength actually is higher. If you towards, wavelength is shorter. So wavelength related with frequency. If your wavelength is decreased, your frequency is higher. That's why ambulance nearer to you, frequency actually is increases. If the ambulance towards to you, frequency is increases. Okay, why? Because V equals to F lambda. This formula, dear, this formula, V equals to F lambda. The speed of the sound from the ambulance is a fixed what? In the air is a constant value. In the air, the sound can be 340 meter per second. It will be constant. So when your wavelength is become short, then your frequency must be become high. Okay? Frequency must be become high. Can we do it in terms of wavelength when explaining? When you're talking about wavelength, you still need to relate back to the frequency because Doppler effect is talking about frequency, how the frequency changes. Okay, Prasan? But it helping us to remember. For me, it helping me to remember I'm starting from the wavelength. How was the wavelength will change? So for me, do you know this slinky spring? This one slinky spring. Okay, let's say I fix at here. Okay, I fix at here. Then I pull my slinky spring away. So fix at here, slinky spring away. So can you see that I will become like this? My wavelength, I assume this is crest to crest or whatever. This is wavelength. Okay, so it will be increases when away. I pull away. My slinky spring, actually the wavelength become longer. Actually, this one is helping me to memorizing. How was the wavelength when we are near or away? So this one I share my idea to you. It's not true to the physics, okay? But we can using the idea, the slinky spring. When it further far away, we pull it far away. So the distance between the slinky spring, it will become higher. So I assume, that is my wavelength. So if away, away at here, you see, this one shows away. So that means here to here, away. I pull my slinky spring away. So can you see that my slinky spring actually having a longer distance? So if towards, okay, if towards here, towards, I push it in towards, so I will get very close to each other, something like that. So my actually, I can helping me to remember my wavelength actually become lower. This is the way how I memorize. I'm sharing with you. Sometimes we study, we need some technique helping us, okay? So this is the way how I memorize. Nearer, so I imagine the slinky spring push towards. So the distance between the slinky spring actually is nearer. So my wavelength become lower. Lower wavelength frequency must be higher. So when move towards to me, frequency is increased. Move away from me, frequency will decrease. Is that clear? Is it okay, dear? Okay, Wesley, okay, Tony, okay, Fawa, okay. Okay, you can use whatever method helping you to memorize. That is my method, using slinky spring to think and imagine. Okay, so we look at here, how we count Doppler shift or Doppler effect. Okay, so we are saying that the frequency that we observe will be changed. It depends on it move towards or away from us. Okay, so at here, this is the formula how we do calculation. So FO is observed. What we observe, what frequency that we observe. Frequency of the source will always unchanged one. From the ambulance, the frequency is always unchanged. Okay, the V is the wave velocity. Okay, then the what? This one, Vs is the velocity for the source. Okay, velocity for the source to the observer. So later on we see how we apply this formula. We go through one by one later on. Okay, but when we do this using this formula, you see plus minus. When I'm going to using plus, when I'm going to using minus. So at here, this one important. Okay, when you are towards to me, you must using minus. When towards to me, we must using minus. Okay, so let me think. Okay, how am I memorize this? Is you are using the slinky spring just now. Okay, towards. So my wavelength becomes shorter. Then my frequency should be higher. Correct? My frequency that I observe must be higher. Okay, if I want to make my FO higher, I should be divided by a small value. This one is my small value. So I should using minus, not plus. I want to get my FO is higher FO, so I need using divided by a small value, so I'm using minus. For me, I'm using this way to memorize. If you got a very good technique to memorizing that two words, we're using minus, then you share with us, okay? We're sharing the technique, okay? For me, moving towards using plus or minus for the bottom part of the equation, I would think moving towards slinky spring nearer to each other, so the wavelength will be decreased. Oh, wavelength decrease, then the frequency that I observe will be increased. Oh, how can I get a bigger frequency observe frequency? I should divide a small value so that my observed frequency will be higher. This is the way how I memorize. But of course, when we do more and more and more question, then it's automatic comes in our mind. Is towards is using minus. Okay, away is using plus. So this one, away is using plus. Okay, so we look at the summary at here. Summary. When away is using plus. So can you see that? Using plus. When closer, move towards, we're using minus. Okay, when moving away from you, can you see that? The wavelength become longer wavelength. So the slinky spring, I pull away. The distance between the slinky spring, the spring, okay, actually increasing. So longer wavelength. Your wavelength longer, your observed frequency will be lower. We're using plus so that at the end your observed frequency actually is smaller value. Okay, if move towards my slinky spring, I compress it, move it towards, so at the end my wavelength is decreased, my observed frequency become higher. In order to get a higher observed frequency, I using minus, so my bottom part divided by a small value, that's why I using minus. Is it okay for this? Then we can go to your page number 3. Now it's learning how we using this formula. Okay, using plus or using minus. Until here, is that clear? Ask me a question. Okay, Wesley, okay. Vashini, okay. Clement, okay. Tony, okay. Haitian, okay. Fatima, okay. Okay, good job. Dear, this one, I don't want to explain first. Until we do this question, then we come back to here. We're trying to practice with this, which is related with just now what we learned now, okay? A toy drone emits a sound. So this one is the frequency, observed frequency or from the source. What do you think? The toy drone emits a sound. This one should be your source. Am I right? This is your source. You are the observer. This is the frequency from the source, okay? Then after that, they say that the speed in the A. So this one is actually your V, speed in the A. Okay? Then after that, the drone move along a straight path directly towards to an observer. Oh, okay, nearer towards. So at here, this one is towards. So you have to think, if towards, okay? So what happened to the frequency? What happened to the wavelength? Okay, then next, continue in a straight line, directly away. Okay, we got divided into two parts. Now it's nearer. Then after that is away. So here is closer. Then after that is away, right? Directly away, yes. The speed of the drone is constant. What is the velocity of the drone? Drone is your source, so Vs is the velocity of your source. So we write Vs. Then what is the frequency? Frequency by the observer, heard by the observer. So they want you to find FO. They want you to find FO. Then they want you what? When the frequency, oh, not asking you to find FO. They tell you FO is 850 hertz. They tell you FO is 550 hertz. What is the velocity of the drone? Okay, FO is equals to V over V, what? Vs, Fs. Okay, here we have to think using plus or using minus. Using plus or using minus, dear? What do you think? Any of you can give me the idea using plus or using minus? Vashini say minus. Wesley say plus because it is away, right? No, it's Prasan say minus. Fatima say minus. Now it's closer. Now it's closer. Okay, coming and closer. Closer, we're using minus. Here, we're using minus. Okay, so we try to do substitution. The source is 550. Then after that, when they asking you here, dear, I know the problem. Why is minus here? Another explanation. Frequency is 850 hertz. Frequency for your observe is greater than frequency of your source, which is 800. 850 hertz is greater than 800 hertz. So can you tell me, right now is towards or away from me? Your FO right now is higher. So actually it's away or towards. This one wavelength become shorter. So it's actually towards or away. Towards. Washini said towards. Kai-Xian said towards. Wesley said towards. Yes, Wesley. That's why we need to using minus is because right now in this case, when 850 hertz, actually this question asking you when it is towards. When it is towards, so what is your VS? What is your VS? So at here, that's why we need to using minus. We need to using minus here. Minus is towards. Okay? Although just now they got mentioned towards and then away. So we want to know which case they want us to answer. They say that when frequency becomes 850 hertz, that means right now they are towards, they are asking for the first part at here, this one. Okay, so at here, V, what is our V? V is 330 minus 330 minus your source. We don't know the source. Times the frequency of the source, 800. So can you count for me? What is your VS? What is your VS? Kai-Chen correct. Prasan towards correct. Washini correct. So at here, it must be towards, because why towards is because your observed frequency is greater than your source frequency. Observed frequency is higher. So I know that actually is towards. Okay, so at here, if you do your mathematics correctly, it should be 19 meter per second. Your answer should be C. Is that clear, dear? Any of you got any question? Good job. So Wesley, okay? Although they're asking for two case, but actually until this sentence, they're only asking you one case. They're asking you when it moved towards. Okay, if okay, then we goes trying to the past year question. We goes to the next page, number 4. Wesley, is it okay, Wesley? Clement, is it okay, Clement? Wesley, okay? Not Wesley asking the question. Just now, who was the one? Let me have a look. Okay, it's fine. We goes to next here. Okay, the siren of the moving car, police car. So emits, that means this is the source. So that means this is frequency of the source. You label Fs. Okay, the stationary observer listen and get hear the sound of frequency this. That means this is from the observer. Observe the frequency Fo. Okay, the speed of the sound is this 340. So this is V. Speed of sound. It's not speed of the siren. Okay, here, what is the speed of the car? The car moving. How fast it moving? So this one is Vs. They're asking you what is your Vs? Source. And what is the direction? Direction using just now the method. Your observed frequency 494 and your source frequency 440. So actually, this is higher. Higher, am I right? It's towards or away. Frequency is higher. Wavelength is shorter. So it's closer or away. Towards or away, dear? Towards or away? Good job. Good job. Towards. Okay? wavelength shorter. So you imagine the slinky spring push nearer, okay? So it's towards. So your answer will be only B or D. Okay, can you try to do calculation and tell me what is your speed of your source? Your source is the car. Okay, your source is the car moving. Car moving. You are the observer. So can you use the formula and do calculation? But the problem is using plus or minus. Towards, we're using minus. Towards, we're using minus. Okay, do your calculation and tell me your answer. Just now got one of your friend already get the answer. Is it Prasan? I think so. Let me have a look. Yes, no. Just now who are the one answer? Kai Qian, correct. Very good. Wawa, correct. Okay, so at here 494 equals to the speed 340 divided by 340 minus Vs times your 440. You don't tell me that you don't know how to move mathematics. It cannot be accepted if you are A level already. Moving mathematics is the basic. So correct, Fatima. Okay, so at here your answer should be 37 ms negative 1. Answer should be B. Okay, so but let me check. Prasan answer correct. Okay, so from here, two questions. We can observe, we can know that what we need to know first. Your observed frequency actually is greater or actually is smaller. Okay, so ask yourself. Read the question and ask yourself. So from here, we can determine is towards or away. If greater, then it is towards. Okay, if less than, the frequency less than, then this is away. So this is the first point. You have to know from the, you have to analyze from the question. Second point, you ask yourself, when you are towards, okay, the formula FO equals to V over V, Vs times Fs. Okay, here, we should using plus or minus. If move towards, we're using minus. How I know I using minus? Because I know from number one, I know already it's moving towards. So I need to using minus. Okay, so for this one, FO equals to V over V, Vs times Fs. So from here, this one is we using plus. How I know? Because it's away. Away, then I using plus. Two things you have to analyze. Two things you have to analyze. FO higher or lower? It become higher or lower? If higher, it towards. Because frequency higher, wavelength becomes shorter. So that means nearer to you, towards. If towards, then here we're using minus. If away, we're using plus. Then we continue solve the question. We do two questions, then we will find that they are using the same technique to solve it. Is that clear? Okay, so today we stop at here. So if you want to try, you may try. If your school already teaching you until this chapter, then you can try by yourself. If not yet, you want to wait, next week we will continue. We will continue our lesson by next week. So, oh, today I haven't take attendance. You don't go first. Wait, dear. Give me 1 minute. Let me take attendance first. Okay, I forget already. Joray here, Prasan here, Vashini, Kaichen, Prasan. Yueting is absent, Fawa, Fatima, okay. Vito, I didn't see Vito. Jahan, I didn't saw. Jahan, Tony, yes. Manjo, also no. Boyang, yes. Wesley, yes. So today we got friends Clement. And then I think Boyang is here. Fawa, Joray, Wesley, Clement. Alicia. Alicia, I'm so sorry. I didn't realize about you. Okay. So finish taking attendance. So that's all for our lesson today. If no question, then we stop our lesson today. Bye bye.